Hello everyone, this is Shubham from Edureka. Topic of today's session is Hadoop YARN. Let me take this opportunity to explain you what is YARN and how it works. We'll first start with Hadoop version 1 where we had MapReduce version 1. So in MRV1, the two core services were HDFS, that is Hadoop Distributed File System, and MapReduce, which forms the basis of almost all Hadoop functionality. All other components are built around these services and must use MapReduce to run Hadoop jobs. While MapReduce method enables user to focus on the problem at hand rather than the underlying processing mechanism, they do limit some of the problem domains that can run in Hadoop framework. So now let us know how MapReduce version 1 works in order to understand its limitations. The MapReduce processing model consists of two separate steps. The first step is parallel map phase, in which input data is split into discrete chunks that can be processed independently. The second phase is the reduce phase, in which the output of map phase is aggregated to produce the desired result. This is simple and fairly restricted nature of programming model, which lends itself to a very efficient and extremely large scale implementation across thousands of low cost commodity servers. When MapReduce is paired with a distributed file system such as HDFS, which can provide high aggregate I/O bandwidth, the economic of the system becomes extremely compelling. This is a key factor in the popularity of Hadoop. One of the key to Hadoop performance is the lack of data motion, such as compute tasks are moved to the server on which the data resides and not the other way around. Specifically, the map task can be scheduled on the same physical nodes on which data resides in HDFS, which exposes the underlying storage layout across the cluster. This design significantly reduces the network input-output patterns and keeps most of the I/O on local disk or on a neighboring server within the same server rack. To understand the new YARN process flow, it is helpful to review the original Apache Hadoop MapReduce design. As a part of Apache Software Foundation, MapReduce has evolved and improved as an open source project. MapReduce project itself can be broken down into the end user MapReduce APIs for programming the desired MapReduce applications, the MapReduce runtime, which is the implementation of various phases such as map phase, sort, shuffle, or merge aggregations, and the reduce phase, and the MapReduce framework, which is the backend infrastructure required to run users' MapReduce application, manage cluster resources, and schedule thousands of concurrent jobs, among other things. This separation of concerns has high significant benefits, particularly for end users, where they can completely focus on their applications via the API and let the combination of MapReduce runtime and the framework deal with the complex details such as resource management, fault tolerance, and scheduling. As you can see in the right hand side image, the master process is the job tracker, which serves as the clearinghouse for all MapReduce jobs in the cluster. Each node has a task tracker process that manages tasks on the individual node. The task tracker are controlled by the job trackers. The job tracker is responsible for resource management, tracking resource consumption, availability, and job lifecycle management like scheduling individual tasks of the job, tracking progress, providing fault tolerance for tasks, etc. The task tracker has simple responsibilities like launch or tear down tasks on order from job tracker and provide task status information to the job tracker periodically. Hadoop MapReduce framework has exhibited some growing pains, in particular with regard to the job tracker, several aspects including scalability, cluster utilization, ability to control upgrades to the stack, and support for workloads other than MapReduce itself. MapReduce is great for many applications, but not everything. Other programming model better serves requirements such as graph processing and iterative modeling using message passing interface. As is often the case, much of the enterprise data is already available in Hadoop HDFS, and having multiple paths for processing is critical and clearly necessary. Furthermore, given the MapReduce is essentially for batch processing, support for real-time and near real-time processing has become an important issue for the user base. A more robust computing environment within Hadoop will enable organizations to see an increased return on their Hadoop investment by lowering their operational cost. Now, the first challenge was scalability. The processing power available in data center continues to increase rapidly. Consider the additional hardware capability offered by a commodity server over a 3-year period. In 2009, we had 8 cores, 16 GB of RAM, and 4 into 1 TB of disk. Coming down to 2012, we have 16 plus cores, 72 GB of RAM, and 12 into 3 TB of hard disk. These new servers are often available at the same price. In general, servers are twice as capable today as they were 2 or 3 years ago. MapReduce is known to scale to production deployment of approximately 5,000 server nodes in 2009 vintage. Thus, for same price, the number of CPU cores, amount of RAM, and local storage available to the user will put continued pressure on the scalability of new Apache Hadoop installations. So the next point is utilization. So in the current system, the job tracker views the cluster as composed of nodes with distinct map slots and reduce slots, which are not fungible. Utilization issues occurs because of map slots might be full while reduced slots are empty, or a vice versa scenario. Improving the situation is necessary to ensure the entire system could be used to its maximum capacity for high utilization and applying resources when needed. Next is user agility. In a real-time deployment, Hadoop is very commonly offered as shared multi-tenant system. As a result, changes to Hadoop software stack affects a large cross-section of enterprise. Against the backdrop, users are very keen to control upgrades to the software stack, as such upgrades have a direct impact on their applications. Now let us discuss a problem that Yahoo faced. Yahoo was the first company to embrace Hadoop in a big way, and it was a trendsetter within the Hadoop ecosystem. In late 2012, it struggled to handle iterative and stream processing system of data on Hadoop infrastructure due to MapReduce limitations. Scalability bottleneck was caused by having a single job tracker. According to Yahoo, the practical limit of such design are reached up to a cluster of 5,000 nodes and 40,000 tasks running concurrently. After implementing Yarn in first quarter of 2013, Yahoo installed more than 30,000 production nodes on Spark for iterative streaming, Storm for stream processing, Hadoop for batch processing, etc. Such a solution was possible only after Yarn was introduced and multiple processing frameworks were implemented. So to address these needs, the Yarn project was started by Apache Hadoop community to give Hadoop the ability to run non-MapReduce jobs within the Hadoop framework. Yarn provides a generic resource management framework for implementing Hadoop applications. In Hadoop version 2.x, MapReduce has undergone a complete renovation. Yarn is also known as MRV2, that is MapReduce version 2. Yarn provides both full compatibility with existing MapReduce application and a new support for virtually any distributed application. The introduction of Yarn does not change the ability of Hadoop to run MapReduce jobs. It does, however, position MapReduce as a merely one of the application frameworks within Hadoop, which works the same way as it did in MRV1. The new capability offered by Yarn is to use the new non-MapReduce frameworks that adds many new features to the Hadoop ecosystem. So as you can see here, in Hadoop 1.x, MapReduce serves two purposes, that is processing paradigm as well as resource management. Now in Hadoop 2.x, Yarn takes all the responsibilities of resource management, or MapReduce or other frameworks can be used as processing paradigms. The fundamental idea of Yarn is to split the two major responsibilities of job tracker, that is resource management and job scheduling or monitoring, into separate daemons, a global resource manager and a per application master. The resource manager and per node slave, the node manager, forms the new and generic operating system for managing applications in a distributed manner. Yarn relies on these three main components for all its functionalities. The first component is the resource manager, which is the arbitrator of the cluster resources. It has two parts, a pluggable scheduler and an application manager that manages user jobs on the cluster. The second component is the per node node manager, which manages user jobs and workflow on the given node. The central resource manager and the collection of node manager creates a unified computational infrastructure of the cluster. The third component is the application master, a user job lifecycle manager. The application master is where the user application resides. Together, these three components provide a very scalable, flexible, and efficient environment to run virtually any type of large-scale data processing jobs. So, the resource manager is the ultimate authority that arbitrates division of resources among all the applications in the system. Per application master is a framework specific entity and is tasked with negotiating for resources from the resource manager and is working with the node manager to execute and monitor the component tasks. The resource manager has a pluggable scheduler component which is responsible for allocating resources to various running applications like capacity, queue, and other factors. The scheduler is a pure scheduler in the sense that it performs no monitoring or tracking of status for the application, offering no guarantees on restarting tasks that are not carried due to either hardware failure or could be application failure. The scheduler performs its scheduling function based on the resource requirement of an application by using the abstract notion of resource container, which incorporates resource dimensions like memory, CPU, disk, and network. The node manager is the per machine slave which is responsible for launching the application containers, monitoring their resources, like CPU, memory, disk, network, and reporting the same to the resource manager. The per application master is responsible for negotiating appropriate resource containers from the schedulers, tracking their status, and monitoring the progress. From the system perspective, the application master runs a normal container. One of the crucial implementation details of MapReduce within the new YARN system is the reuse of existing MapReduce framework without any major surgery. This step was very important to ensure compatibility of existing MapReduce applications and users. Now, the major benefits of YARN is increased scalability, better memory utilization with containers, and the third one is other frameworks can be integrated like Spark, Storm, Hive, etc. Now, by adding new functionalities, YARN brings new components into Apache Hadoop workflow. These components provides finer grained control for the end user and simultaneously offer more advanced capabilities to Hadoop ecosystem. Let's look at them one by one. So first is Resource Manager. As mentioned earlier, the YARN Resource Manager is primarily a pure scheduler. It is strictly limited to arbitrating requests for available resources in the system made by competing applications. It optimizes the cluster utilization, like keep all resource in use all the time, against various constraints such as capacity guarantees, fairness, and SLAs. To allow for different policy constraints, the resource manager has a pluggable scheduler that enables different algorithms such as those focusing on capacity and fair scheduling to be used as necessary. So as we discussed, resource manager has two components, that is scheduler and application manager. So the scheduler is responsible for allocating resources to applications and does not offer guarantees about restarting failed tasks. Scheduler also have pluggable policies, that is capacity scheduler or a fair scheduler, etc. Moving down to application manager is responsible for accepting job submission, negotiating with the first container for executing the application specific application master, and it also provides the service for restarting the application master on failure. Next is Node Manager. The Node Manager is YARN's per node worker agent taking care of individual compute nodes in Hadoop cluster. Its duties include keeping up to date with Resource Manager, overseeing application containers lifecycle management, monitoring resource uses like memory, CPU, network, etc. of individual containers, tracking node health, log management, and auxiliary services that may be exploited by different YARN applications. On startup, the node manager registers with the resource manager. It then sends heartbeat with its status and waits for the instruction. Its primary goal is to manage application containers assigned to it by the resource manager. YARN containers are described by a container launch context, that is CLC. This record includes a map of environment variables, dependencies stored in remote accessible storage, security tokens, payload for node manager services, and the command necessary to create the process. After validating the authenticity of the container lease, the node manager configures the environment for the container, including initializing its monitoring subsystem with a resource constraint specified application. The node manager also kills container as directed by the resource manager. Now, next is application master. So application master is an important concept in YARN. The application master is in effective an instance of the framework specific library and is responsible for negotiating resources from the resource manager. It is also working with the node manager to execute and monitor the containers and their resource consumption. It has the responsibility of negotiating for appropriate resource containers from the resource manager, tracking their status and monitoring progress. The application master is the process that coordinates an application's execution in the cluster. Each application has its own application master, which is tasked with negotiating resources from resource manager and with the node manager to execute and monitor the task. In YARN design, MapReduce is just one application framework. This design permits building and deploying distributed applications using other frameworks. Once the application master is started, it will periodically send heartbeats to resource manager to affirm its health and to update the record of its resource demands. After building a model of its requirement, the application master encodes its preferences and constraints in a heartbeat message to the resource manager. In response to subsequent heartbeats, the application master will receive a lease on container bounds to allocation of resources at the particular node in the cluster. Depending on the containers it received from the resource manager, the application master may update its execution plan to accommodate the excess or lack of resource. Container allocation or deallocation can take place in dynamic fashions as an application progresses. The application master design enables Yarn to offer some important features like scalability. The application master provides much of the job-oriented functionality to the job tracker so that the entire system can scale more dramatically. Simulations have shown that jobs may scale to 10,000 node clusters composed of modern hardware without any significant issue. As a pure scheduler, the resource manager does not have to provide fault tolerance of resources across the cluster. By shifting fault tolerance to application master instance, control becomes local rather than global. Second is moving all the application framework specific code into the application master generalizes the system so that it can now support multiple frameworks such as MPI, that is message passing interfaces, and graph processing. In reality, every application has its own instance of an application master. However, it is completely feasible to implement an application master to manage a set of applications. Furthermore, this concept has been stressed to manage long-running services which manage their own applications. Example, launching HBase in Yarn via a special HBase app master. So you can go ahead and see the responsibilities of application master, that is managing the application lifecycle, making dynamic adjustment to resource consumptions, managing execution flow, managing faults, providing status and metrics to the resource manager, interacting with NodeManager as well as resource manager, and so on. So next component is containers. Yarn has a pluggable scheduling component. Depending on the use case and user needs, administrator may select either a simple, that is first in first out capacity, or a fair share scheduler. The scheduler class is set in yarn default.xml file. At the fundamental level, a container is a collection of physical resources such as RAM, CPU, cores, and disk on a single node. There can be multiple containers on a single node. Every node in the system is considered to be composed of multiple containers of minimum size of memory and CPU. The application master can request any container so as to occupy a multiple of minimum size. A container is supervised by the node manager and scheduled by the resource manager. Each application starts out as an application master, which is itself a container, often referred as container 0. Once started, the application master must negotiate with the resource manager for more containers. Container requests can take place in a dynamic fashion at runtime. For instance, a MapReduce job may request a certain amount of mapper containers. As they finish their task, it may release them and request more reducer containers to be started. Now, as we have already discussed, yarn containers are described by a container launch context, that is CLC. So, this record includes a map of environment variables, dependencies stored in remotely accessible storage, security tokens, payload for node managed services, and the command necessary to create the process. So, a CLC includes everything that you need to launch a container. Moving ahead, let us understand the yarn workflow. So in earlier Hadoop versions, each node in the cluster was statically assigned the capability of running a predefined number of map slots and a predefined number of reduce slots. The slots could not be shared between maps and reduces. The static allocation of the slot wasn't optimal because slot requirements vary during the MapReduce application lifecycle. Typically, there is a demand of map slots when the job starts, as opposed to the need of reduced slots towards the end of the job. The resource allocation model in Yarn addresses the inefficiencies of static allocation by providing a greater flexibility. As discussed previously, resources are requested in form of containers, where each container has a number of non-static attributes. Yarn currently has attribute support for memory and CPU. The generalized attribute model can also support things like bandwidth or GPUs. So, first, let's look at the client resource request. So, as you can see, a Yarn application starts with a client resource request. A client communicates with the application manager component of the resource manager to initiate this process. The client must first notify the resource manager that it wants to submit an application. The resource manager responds with an application ID and information about the capabilities of the cluster that will aid the client in requesting resources. Next, the client responds with an application submission context. The application submission context contains the application ID, user, queue, and other information needed to start the application master. In addition, a CLC, that is container launch context, is sent to the resource manager. As we already have discussed about CLC, that it contains job files, security tokens, resource requirements, and other information needed to launch an application master on the node. Once the application has been submitted, the client can also request the resource manager kill the application or provide status report about the application. When the resource manager receives the application submission context from a client, it schedules an available container for the application master. If there are no applicable containers, the request must wait. If a suitable container can be found, then the resource manager contacts the appropriate node manager and start the application master. As part of this step, the application master RPC port and tracking URL for monitoring the application status will be established, using which your client can see the application status. In response to the registration request, the application master will send information about the minimum and maximum capabilities of the cluster. At this point, the application master must decide how to use the capabilities that are currently available. Based on the available capabilities reported from the resource manager, the application master will request the number of containers. The request can be very specific, including containers with multiple of resource minimum values. The resource manager will respond as best as possible to the request with container resources that are assigned to the application master. As a job progresses, heartbeat and process information is sent from the application master to the resource manager. Within these heartbeats, it is possible for the application master to request and release containers. When the job finishes, the application master sends the finish message to the resource manager and exits. Next is application master and container communication. At this point, the resource manager has handed off control of assigned node managers to the application master. The application master will independently contact its assigned node managers and provide them the container launch context that includes environment variables, dependencies located in remote storage, security tokens, and commands needed to start the actual process. Next, the node manager launches the container. When the container starts, all data files, executables, and necessary dependencies are copied to local storage on the node. Dependencies can potentially be shared between containers running the application. Once all containers have started, their status can be checked by the application master. The resource manager is absent from the application progress and is free to schedule and monitor other resources. The resource manager can direct the node manager to kill containers. Expected kill events can happen when the application master informs the resource manager of its completion, or the resource manager needs nodes for other applications. When a container is killed, the node manager cleans up the local working directory. When a job is finished, the application master informs the resource manager that the job is completed successfully. The resource manager then informs node manager to aggregate logs and clean up container specific files. The node manager are also instructed to kill any remaining containers, including the application master, if they have not already exited. Now let us quickly move ahead and look at the summary of the YARN application workflow. So first, client submits an application to the resource manager. Then resource manager allocates the container and starts the application master. Then application master registers the container with resource manager. Second, the application master asks for the containers from resource manager. Moving ahead, application master notifies node manager to launch containers. Application code is executed in containers. Then client contacts resource manager and application master to monitor the application health. At last, application master unregisters with the resource manager and leaves all the resources acquired by it. So let us now quickly understand how YARN works. Let's go to VM. So this is our VM. I'll be executing a simple word count example. So let us go to our Hadoop home. In share, Hadoop MapReduce. So we have a sample Hadoop MapReduce examples. So in this jar, we have a word count file which we can execute and check the status of YARN. But before that, I'll show you the HDFS. So this is the HDFS. You can see we have one data node. Let us browse the file system. So this is the word count underscore input.txt file which I'll be giving as input for the word count. If you are not having any file on your HDFS, you can go ahead and execute put command. So let us quickly go ahead and execute this command. The command is Hadoop jar, then the name of the jar file, that is Hadoop MapReduce examples. The name of the class is word count, and then we'll give the input file, that is, let me tally it, word count underscore input.txt, and the output files will be stored in output directory, which is in the root of HDFS. So let us quickly go ahead and execute this command. Meanwhile, we'll go to our yarn web UI, that is 8088. So this is the yarn web UI. As you can see, this is the application that we are executing. This is the application ID, the user, so the name of the application, that is word count, type of application. Again, the status is accepted, final status is undefined. There is one container running, allocated CPU vcores is 1. And here you can track the progress of the application. This is the tracking UI. Let us go to the tracking UI. So state is succeeded. Let us go back to our terminal. As you can see, the program has been successfully executed. You can also see the parameters over there, like number of bytes to be read, number of bytes to be written, number of read operations, the number of write operations. Again, you can figure out the MapReduce framework, how many number of map input records, number of map output records, and then we have all the MapReduce details over here. So let's not worry about them. So it gives you all the details related to that job which you have executed. You can see the log files that has been created while executing this job. You can also track it on your web history server, that is localhost 19888. So again, you can see this word count job, and you can again track the details, that average map time, shuffle time, average reduce time. So these are the details, guys. Let us go to our HDFS browser and look at the output file that has been created. So this is the output file. Let's go ahead and download it. So as you can see, the number of count for car is 4, deer is 3, and the river is 2. So this is the output that we received. I've given a simple input file. Let me show you the file as well. This is the input which we have given, and this is the output which we have received. So that's it. So that's all for today's session. Hope that you found this session helpful and informative. Thank you and have a nice day.